The Great Pyramid is aligned to true north with near-perfect accuracy. How ancient surveyors achieved global precision without modern tools is one of history's greatest puzzles. By the end of this journey, you will understand the forgotten methods that let civilizations map continents and align monuments to the stars using nothing but rope, shadow, and observation. We will uncover how they measured the Earth itself and why some of their stone calendars are more accurate than our own. What does it truly mean to see the world not with satellites, but with the naked eye and a brilliant mind? That near-perfect alignment was not an isolated feat of luck. It was the product of a systematic, repeatable craft, a discipline refined over generations. To grasp the true scale of their achievement, we need to step back and see the world as they saw it. Forget the satellite view, the gridded map, the precise coordinates we take for granted. Their canvas was the raw earth itself, a sprawling, irregular, and often unforgiving landscape. Their challenge was monumental in the most literal sense. They sought to measure distances that stretched beyond the horizon, to lay out foundations that would stand for aligned to the sun or stars, and to create maps that could guide a traveler from one river valley to another across hundreds of miles. They did this without a shared global rulebook for measurement, without a telescope, and certainly without a signal from space. So what did global precision mean to them? It was not the abstract pin on a digital map we think of today. It was a practical, sacred, and deeply cultural necessity. Precision meant a temple doorway that would catch the first light of the solstice sunrise year after year, a signal to begin planting. It meant a canal that maintained a gentle, consistent slope across miles of desert to bring life-giving water. It meant a trade route map etched on a clay tablet that could reliably guide a merchant from Memphis to Thebes. Their benchmark for success was repeatable accuracy for a specific, vital purpose, whether that purpose was honoring the gods, feeding a city, or connecting an empire. The fundamental problems they faced were immense. How do you measure a straight line over a hill or across a river? How do you ensure that line points precisely north when your only reference is the night sky? How do you even agree on what a unit of measurement is when the king's forearm might be a different length from the pharaoh's? This was the chaotic, beautiful reality they had to tame, and their first tools were not made of bronze or stone, but of observation and unwavering patience. Their first and most reliable compass was not a magnetic needle, but the vault of the night sky itself. For ancient surveyors, celestial navigation was far more than a method for crossing oceans. It was the fundamental first principle for imposing order on the chaos of the land. They understood that while the earth beneath their feet was unpredictable, the heavens above were governed by a majestic, unbreakable rhythm. The sun, moon, and stars moved in cycles so consistent they could be predicted for generations. This wasn't just observation, it was a profound realization. The cosmos provided a fixed, universal reference frame that every culture, from the deserts of Egypt to the plains of Mesopotamia, could access and agree upon. By mastering these cycles, they could answer the two most critical questions for any large-scale project. Which way is true north, and when is the right time to begin? The answer to the first question often came from a single, steadfast star. In the northern hemisphere, the star we call Polaris, the North Star, holds a special position. Because of the Earth's rotation, all other stars appear to wheel in great circles across the sky, but Polaris remains almost motionless, marking the celestial North Pole. Finding it was a matter of patient observation. They would identify the constellation we call the Big Dipper and follow an imaginary line through the two stars at the front of its bowl. That line pointed directly and reliably to the North Star. Once that fixed point in the heavens was established, they could translate it to the ground. A simple but brilliant method involved driving two stakes into the earth some distance apart, aligned as best one could guess with that celestial marker. By sighting from one stake past the other to the North Star, and then adjusting the stakes minutely over several nights, they could create a terrestrial line pointing precisely to true north. This line became the sacred axis, the immutable foundation from which every other measurement on a site could be derived. But the sun was their other great architect. Its path changes throughout the year, arcing high in the summer sky and low in the winter. Yet there are 2 days where it reaches its extreme limits, the solstices. On the summer solstice, the sun rises at its farthest point north of east, and on the winter solstice at its farthest point south. These turning points were not just seasonal markers, they were cosmic events etched in stone. A surveyor could mark the sunrise point on the horizon on the summer solstice, and again on the winter solstice. The exact midpoint between those 2 points on the horizon gives you due east. This is how temples like Karnak in Egypt or stone circles like Stonehenge in England achieved their breathtaking solar alignments. They weren't just pointing at the sun, they were conversing with its entire annual journey, capturing its extremes to find the perfect center. This celestial mastery created a cosmic blueprint. A city planned with streets aligned to the cardinal directions was not just orderly, it was in harmony with the universe. A temple doorway designed to be illuminated only on the dawn of the equinox transformed a building into a calendar and a divine signal. The agricultural cycle itself was tied to these observations, telling farmers exactly when to plant and when to harvest. So before a single foundation stone was laid, before the first length of rope was stretched, the ancient surveyors had already drawn their plans across the sky. They had used the infinite, predictable clockwork of the cosmos to establish direction and time on Earth. But with that celestial framework in place, a much more tangible challenge remained. How do you take that perfect line drawn from the stars and physically extend it for miles across rolling hills, through forests, and over rivers, using nothing more than simple tools and human ingenuity with the stars providing their fixed directions? The next challenge was to translate that celestial order onto the uneven ground. This is where the ancient surveyors' true genius became tangible. They turned to a language of pure form and ratio, the timeless principles of geometry. But forget the complex equations and abstract theorems of a modern classroom. For them, geometry was a physical craft, a hands-on art performed with rope, wood, and shadow. It was through the elegant application of a few simple shapes that they tamed landscapes and planned cities. The most fundamental problem in laying out any structure, from a humble house to a vast temple complex, is establishing a perfect right angle. Our modern builder's square is a direct descendant of their solution, a method so reliable it still bears their name, the Egyptian triangle. They discovered that if you create a triangle with sides in the ratio of 3 to 4 to 5, the angle opposite the longest side will always be a perfect 90 degrees. The practical application was beautifully straightforward. A surveyor's crew would take a long rope, knotting it into 12 equal segments. They would stake one end at the corner point of their intended building. One worker would hold the rope at the 3rd knot, another at the 7th knot, which is 3 plus 4, and a third would pull the rope taut from the starting stake out to the 12th knot. When the rope was stretched tight, they had created a massive 3-4-5 triangle right on the ground. The line from the stake to the person at the 4th knot and the line from the stake to the person at the 7th knot were now perfectly perpendicular. They could then extend these lines indefinitely using rows of stakes, creating the flawless square or rectangular grids we see in ancient foundations. This was mathematics made physical, a theorem you could walk around. But geometry's power extended far beyond creating corners. It allowed them to measure what seemed immeasurable, like the width of a river or the height of a cliff, through a technique called triangulation. Imagine standing on one bank of a wide river, needing to know the distance to a specific tree on the far side. You couldn't simply stretch a rope across. Instead, you would mark your starting point on your side. Then, you would walk a known distance along the bank, keeping the line as straight as possible using sighting poles, and mark a second point. You now have the length of one side of a triangle on your side of the river. From each of your 2 points, you would use a simple sighting tool, like a notched stick or a hanging plumb line, to measure the angles to the tree across the water. With one side length and 2 angles known, the entire triangle is defined. The principles of similar triangles, understood intuitively long before they were formally written down, allowed them to calculate the river's width without ever getting their feet wet. This same logic, scaled up to a staggering degree, was used to achieve one of antiquity's most breathtaking intellectual feats, measuring the entire planet. The Greek scholar Eratosthenes, head of the Great Library of Alexandria, performed this calculation around 2,200 years ago. He knew that on the summer solstice at noon in the city of now Aswan, the sun shone directly overhead, casting no shadow at the bottom of a deep well. On the same day and time in Alexandria, roughly 500 miles to the north, a vertical obelisk did cast a shadow. Eratosthenes measured the angle of that shadow. It was about 7.2 degrees, which is 1/50th of a full circle. He realized this angle difference must correspond to the curvature of the Earth between the two cities. Therefore, if 500 miles represented 1/50th of the Earth's circumference, the total circumference must be 50 times that distance, or about 25,000 miles. His result was astonishingly close to the actual value. He achieved this not with satellites, but with geometry, observation, and a brilliant grasp of scale. He understood the Earth was a sphere and used a local shadow measurement to deduce a global dimension. This was the ultimate expression of their craft, using simple tools and profound reasoning to comprehend the world itself. These geometric principles, from the humble 3-4-5 triangle to the grand calculation of the Earth, were the invisible frameworks upon which empires were built. They enabled the precise canal systems of Mesopotamia, the arrow straight roads of the Romans, and the celestial alignments of countless temples. But establishing direction and mastering geometry still left one monumental practical problem. How do you physically transfer a perfect plan from a small diagram onto miles of rugged, unpredictable terrain, ensuring that every foundation stone, every column, is placed exactly where it needs to be? Geometry gave them the angles and lines on paper, but the Earth itself is rarely flat or still. To build on a monumental scale, they needed to conquer the third dimension, to master the concepts of level and elevation across vast distances. Their solution was to turn to the most patient and reliable force in nature, water. In a world without laser levels or digital inclinometers, water's unwavering search for equilibrium became their universal standard for true horizontal. The principle is beautifully simple. Pour water into a connected series of trenches or channels, and the surface will always settle to the same level, regardless of the uneven ground beneath. This was the ancient spirit level, a tool of profound accuracy. To level the foundation for something as immense as a pyramid, surveyors would dig a shallow network of channels around the entire perimeter of the site and fill them with water. By marking the water line at numerous points on the channel walls, they created a continuous horizontal datum, a baseline etched into the Earth itself. From these marks, they could measure down with plumb bobs to ensure every foundation stone was set to the exact same depth, or measure up to guarantee the rising courses of stone remained perfectly level. This same principle guided the engineers of vast canal projects. To ensure life-giving water would flow gently but steadily across miles of desert, they used these water trenches to establish a consistent, almost imperceptible slope. A drop of just a few inches per mile, meticulously maintained using water's own level as a guide, could mean the difference between a thriving agricultural region and a failed, stagnant ditch. Water did not just give them level, it gave them direction and life. But while water mastered the horizontal plane, another elemental force helped them map their place on the planet itself, the sun and its shadow. The Gnomon, a simple vertical rod stuck into the ground, is perhaps the most understated precision instrument in history. Its changing shadow was a clock, a calendar, and a global positioning device. By tracking the shadow's path throughout the day, they could mark local noon, the moment the shadow pointed true north or south. By observing the shadow's length at noon over the course of a year, they could pinpoint the solstices, the longest and shortest shadows marking the sun's turning points. This was the practical, daily application of their celestial knowledge, but the Gnomon held a deeper secret about the shape of the world. Ancient travelers and scholars noticed something curious. The length of the noon shadow on the same day, say the equinox, was different in the city of Alexandria than it was to the south. This difference in shadow angle, measured with nothing more than a stick and some basic geometry, directly revealed their difference in latitude. It told them how far north or south they were on the Earth's curved surface. A larger shadow angle meant they were farther from the sun's direct path, meaning farther north or south. By sharing these measurements across great distances, they could begin to sketch lines of latitude on their maps, creating a rudimentary but effective global grid long before the invention of the sextant. This humble stick, casting its silent, moving line on the ground, connected a local observation to a planetary scale. It embodied their entire philosophy, that profound truth could be found by paying meticulous attention to the simple, repeating patterns of the natural world. They didn't need to invent complex machinery, they needed to understand the machinery that already existed all around them. With the power of water to find level and the intelligence of a shadow to find place, they possessed the core toolkit to shape the world. Yet, even with perfect alignment, flawless geometry, and true levels, one final, human challenge remained. How do you ensure that the grand vision in the master surveyor's mind is executed with perfect fidelity by hundreds of workers across a sprawling, chaotic construction site that might take decades to complete, yet the grandest plan is useless if the builder's measuring rod disagrees with the stonemasons? For a project spanning generations and involving thousands of hands, a shared language of measurement was as vital as the blueprint itself. This language did not come from an abstract decree, but from the most accessible instrument of all, the human body. The Egyptian cubit was the length from a man's elbow to the tip of his middle finger. The Roman pace was one full stride, from where one heel left the ground to where it landed again. The Greek was based on the length of a racecourse, measured in footsteps. These were intuitive, living units, born from repetitive motion and the scale of the human form. You could literally carry your ruler with you, but this created an obvious problem. My forearm is not the same length as yours, and my stride changes if I am tired. If every worker used their own personal cubit, the pyramid's sides would wander into chaos. The solution was a master standard, a physical embodiment of the perfect unit, kept under sacred guard. In Egypt, this was the royal cubit rod, meticulously crafted from granite or hard wood and housed in the temple precincts. These master rods were not arbitrary. They were often subdivided with exquisite precision into smaller units like palms and digits, creating a consistent decimal-like system. Craftsmen and overseers would then create their own wooden or metal cubit sticks, calibrated directly against the official standard. This process of chain calibration meant that even though the original reference was based on a human dimension, its replication was controlled and exact. The rhythm of the human body also provided units of distance for mapping the wider world. The Roman mile, the passus, was simply 1,000 paces of a legionary. Surveyors laying out the arrow-straight Roman roads would often employ trained pacers, soldiers who could maintain a remarkably consistent stride length over miles of terrain, counting their steps to measure distances with surprising reliability. This idea of standardizing a natural human scale unit was a stroke of administrative genius. It meant that a foreman in the quarry, cutting a block to be 10 cubits long, and an architect at the construction site, marking out a 10-cubit foundation trench, were both envisioning the exact same length, even if they were miles apart and had never met. It translated abstract design into a shared physical reality for every person on the project. The consistency achieved is etched in stone. Measurements of the Great Pyramid's base reveal a margin of error of less than 0.2% across its entire 750-foot side, a testament to the fidelity of that royal cubit standard over decades of construction. This was more than mere standardization, It was the creation of a communal rhythm. When an entire society builds with the same cubit, that unit becomes embedded in the culture's architecture, art, and even thought. It creates a harmony of proportion, a visual language where buildings feel intuitively scaled to the people who use them. The human body, therefore, was not just the tool, but the very template for imposing order on the world. Yet, with a celestial framework, geometric principles, and a standardized language of measure, these ancient surveyors still faced their ultimate test of precision, one that required them to think not in miles, but in. Standing on the windswept Salisbury Plain, the great stone circles seemed to speak a language of pure geometry written against the sky. Stonehenge is not merely a collection of massive rocks. It is a three-dimensional astronomical diagram carved into the earth by Neolithic surveyors over 4,000 years ago. Their achievement here distills every principle we have explored: celestial observation, geometric planning, and painstaking physical execution, into a single, hauntingly precise monument. They accomplished this without metal tools, without written records, and with an understanding of the cosmos that feels almost impossibly profound. The central axis of Stonehenge, running through the heart of the monument, is aligned to the summer solstice sunrise in one direction and the winter solstice sunset in the other. To grasp the scale of this feat, we must step away from our modern conception of a construction site. This was not a project with a single architect and a detailed blueprint. It was a cultural endeavor spanning centuries, likely passed from one generation to the next through oral tradition, song, and ritual. The knowledge of the sun's turning points was not abstract science. It was sacred narrative, a story of life, death, and rebirth etched into the very horizon. So how did they find these precise points on a landscape with no permanent landmarks? The process began with patient, generational observation. Long before the first sarsen stone was raised, their ancestors likely used simple wooden posts driven into the chalky soil. Over years and decades, they would have marked the furthest northernmost point on the horizon where the sun rose in June, and the furthest southernmost point where it set in December. These were not quick measurements, but rituals repeated annually, confirming the sun's slow dance until its extreme limits were memorized by the community. The midpoint between these two extremes would give them an east-west line, but the solstice alignments themselves held the deepest meaning. Translating those observed horizon points into the massive stone architecture required a different kind of genius, one of practical geometry and sheer physical effort. The initial layout of the monument, including the circular bank and ditch, and the iconic holes that form its earliest phase, demonstrates a sophisticated understanding of the circle. Creating a perfect, large-diameter circle on open ground with only ropes and stakes is a geometric puzzle. Researchers suggest a method where a central stake was placed, and a long rope, acting as a radius, was used to scribe the entire circumference by simply walking in a circle and marking the ground. This simple act creates a perfect geometric form, a boundary between the ordinary world and a sacred, ordered space. But the true marvel is how the larger sarsen stones, those towering uprights capped with lintels, were positioned to frame the solstice events. This was surveying at its most ambitious. After quarrying and transporting these colossal stones from miles away, the builders faced the ultimate test of alignment. Using siding poles placed along the intended axis, they would have painstakingly adjusted the placement of each massive stone hole. The goal was to ensure that when viewed from the center of the circle, the narrow gap between two specific uprights perfectly framed the first sliver of the solstice sun as it crested the horizon. This is precision engineering of light and shadow. A miscalculation of even a single degree over that distance would mean the spectacle would fail, the sun appearing off to the side, breaking the sacred promise of the architecture. The consistency of these alignments across the centuries-long construction of Stonehenge tells us something crucial. It was not luck. It was the result of a deeply embedded, communal knowledge system. The surveyors and builders of each generation were the custodians of a celestial template, a living memory of the horizon points that guided their ancestors. They used ropes to translate memory into geometry and backbreaking labor to translate geometry into eternal stone. When the dawn of the summer solstice finally illuminated the heart of the completed circle, it was the validation of a promise made hundreds of years prior. It proved that human beings, working together across generations with nothing but careful observation and determined will, could capture a moment of cosmic time and hold it still. This stone calendar did not just tell the date, it performed it, creating a direct, visceral connection between the community and the cycles that govern their world. Yet, if a monument like Stonehenge represents a localized, celestial observatory, it prompts a staggering question. How far did this ancient understanding of precision truly reach? Could these methods, born from watching the sun and stars, be applied to something as vast and seemingly chaotic as mapping an entire continent? The silent stones of Stonehenge hold a conversation with the sun. But on the sands of Giza, an even more precise dialogue was etched in limestone. The Great Pyramid does not just align to the cardinal directions, it defines them. Its base is oriented to true north with an accuracy that still defies easy explanation, an error of just 3/60ths of a single degree. To understand that number, picture the hour hand of a clock. That tiny sliver of error is less than the distance the hand moves in one single second. This was not an approximation, it was a statement of intent, achieved over 4,500 years ago. So how was it done? The answer lies in a perfect fusion of celestial observation, simple yet brilliant tools, and a process where technical act became sacred rite. The prevailing theory points to the ancient Egyptians mastering the night sky, specifically the circumpolar stars. Unlike the sun which rises and sets, these stars, close to the celestial pole, never dip below the horizon. They wheel in a continuous, predictable circle around the North Point. By observing not one, but two of these stars as they cross the meridian, the imaginary north-south line in the sky, a surveyor could find a far more accurate fix than using a single star. Imagine a forked stick held upright. When one chosen star was seen at its highest point directly over one fork, and another star was seen at its highest point over the opposite fork, the line between those two sighting points on the ground would point almost perfectly north. This method, using the simultaneous transit of two stars, cancels out minor atmospheric distortions and human error, yielding a result of breathtaking precision. The tool they likely used for this is known as a merkit. It was a simple device, often a horizontal bar with a plumb line hanging from it, used alongside a sighting tool made from a palm rib with a slit in it. By aligning the plumb line with a star through the slit, they could track its path with remarkable consistency. But this celestial observation was only the first, intellectual step. The physical act of transferring that perfect north line from the night sky onto the sprawling, dusty construction site was a ceremony in itself, known as the stretching of the cord. This was far more than a surveying technique. It was a ritual presided over by the goddess, the divine scribe and mistress of builders. In temple reliefs, we see the pharaoh and the goddess together, hammering stakes into the ground and stretching a cord between them to lay out the foundations of a temple. This ritual transformed a practical task of measurement into a sacred act of creation, aligning the earthly construction with cosmic order, or T. The technical process behind the ritual was equally meticulous. After establishing their true north line using the stars and the merkit, surveyors would have driven two primary stakes into the desert floor along that alignment, very far apart. Then, using a long, uniformly taut rope, they would have created a series of perpendicular lines off this primary axis, effectively gridding the entire massive base area. They would check and recheck these lines over many nights, adjusting the stakes by minute amounts as their celestial observations refined the master alignment. The final verification likely came with the rising of Sirius, the star associated with the Nile's life-giving flood. If the pyramid's eastern face was perfectly aligned to catch the first gleam of Sirius at a specific time of year, it confirmed that the structure was in harmony with both the cycles of the sky and the rhythms of the earth. This seamless blend of astronomy, geometry, and spirituality is what made the precision possible. The 3/60ths of a degree error is not a failure, but a testament to the limits of their physical materials. Over a base length of over 750 feet, that tiny angular error translates to a physical misalignment of less than 2 inches from corner to corner. The stones themselves, settling over, or the imperceptible shift of the underlying bedrock could account for it. The intent and the achieved reality was as close to perfect as human hands could make it. They were not just building a tomb, they were anchoring a symbol of eternal order to the very axis of the world. Yet, this obsession with celestial alignment raises a profound and haunting question. If ancient cultures from Britain to Egypt could achieve such localized precision, did they possess a larger, more connected understanding of the world's shape? Could they see their individual sacred sites as points on a grand, global geometry? We are only beginning to recognize the precision of Giza and Stonehenge speaks to a mastery of place. But on the arid plains of southern Peru, an ancient people performed a feat of surveying that seems to defy human scale. The lines are a gallery of giants, etched into the desert pavement over 2,000 years ago. Here, straight lines run for miles, arrows straight across valleys and over hills, while immense geometric shapes and stylized animals, a hummingbird, a spider, a monkey, sprawl across the earth, their forms only fully comprehensible from a vantage point high above. This was not architecture to be walked through, but art to be witnessed, perhaps by the gods themselves. The central mystery is not their purpose, which remains a subject of respectful study, but their method. How did the surveyors, without flight or modern optics, plot and execute these colossal designs with such clean, unwavering accuracy? The answer lies not in magic, but in a brilliant, scaled-up application of the same principles we have seen elsewhere, adapted to a vast and unforgiving canvas. The first challenge was the line itself. Creating a straight path over 5, 10, or even 30 miles of rolling desert terrain seems impossible without a laser or a theodolite. Yet their solutions were elegantly simple and grounded in direct observation. One compelling theory involves the use of a series of aligned sighting poles. A master surveyor would first establish the desired line's starting point and direction, possibly using celestial markers or prominent mountain peaks on the horizon as a guide. A team would then place a tall wooden pole at that starting point. A second worker would walk directly away, perhaps a mile or more, until they were nearly at the limit of clear visibility. They would then plant a second pole, carefully aligning it so that from the first pole's position, it appeared to perfectly cover the distant horizon marker. This process would be repeated, pole after pole, in a human chain of alignment. From each new pole, the worker would look back to ensure it was still in perfect line with all the previous poles stretching behind them. This method of sequential sighting, using the human eye as the judge, could create a series of straight segments that, when connected, formed a line of astonishing precision over immense distances. To clear the path, they simply removed the dark, sun-baked stones from the desert surface, exposing the lighter colored soil beneath, creating a stark contrast visible for miles. But the truly mind-bending creations are the complex biomorphic figures. How do you enlarge a small sketch of a hummingbird into a perfect, 500-foot-long rendering on the ground? The most plausible explanation involves a master plan and a system of proportional scaling, a technique still used by artists and engineers today. Archaeologists suggest the artists likely first designed these figures at a manageable scale, perhaps on a small plot of prepared ground or even on a textile. This model would be carefully subdivided into a grid of squares. They would then establish a much larger proportional grid across the chosen section of the desert floor, using ropes and stakes to mark it out. Each curve, line, and detail from a single square on the small model would then be meticulously transferred, or upscaled, into the corresponding, much larger square on the desert grid. It is a painstaking process, but one that relies on simple coordination rather than advanced mathematics. A team leader at the large grid could call out instructions, like move the marker 10 units right and 5 units up from this corner, and workers on the ground would execute it. By working square by square, a small team could faithfully reproduce a gigantic image without anyone ever needing to see the overall form. This method explains the remarkable consistency and clean, continuous lines of the figures, even across subtle dips and rises in the landscape. The final, profound element of their technique was an intuitive mastery of perspective and proportion from a single, fixed viewpoint. Some researchers propose that they may have used the surrounding foothills as natural observation platforms. A team leader positioned on a slope could oversee the work below, guiding the adjustment of lines to ensure they appeared correctly proportioned from that specific vantage point. This suggests the designs were intended to be viewed not from directly overhead in the modern sense, but from a designated sacred space in the surrounding hills, making the gods or ancestral spirits the audience for this monumental performance. The creation of the lines was therefore a communal act of faith and precision, a ritual of making marks so large they became a permanent part of the land itself. It demonstrates that ancient surveyors could think in multiple scales simultaneously, from the intimate grid square at their feet to the monumental form taking shape across the valley, all held together by shared knowledge, coordinated labor, and a deep connection to the terrain. This ability to project immense, precise patterns onto the earth hints at a worldview where the landscape itself was a page to be inscribed. Yet, it prompts an even broader question. If individual cultures could map their local heavens and their immediate terrain with such exactitude, did any of them ever attempt to connect these dots on a truly continental scale, to draw a map of the world as they knew it while they inscribed visions onto the desert? Other civilizations were solving a more urgent puzzle: how to draw the world itself. The leap from aligning a single temple to mapping continents required a new kind of thinking, one that traded perfect celestial alignment for practical knowledge of distance and direction on a human scale. The earliest known attempt to answer the question of what the world looks like comes from a cracked tablet of clay. The Babylonian World Map, created around 2,500 years ago, is not a geographical chart as we know it, but a powerful schematic, a cognitive snapshot of their entire universe. At its center lies a circle labeled Babylon, with the Euphrates River cutting vertically through it. Around this, a ring of ocean forms the known world's boundary, and beyond that ocean, 8 triangular regions are drawn, labeled simply as distant lands. This map was never meant to guide a traveler from one city to the next. Its purpose was philosophical and administrative, to visually organize the cosmos according to Babylonian understanding, placing their empire literally at the center of creation. It represents a foundational step in surveying, the translation of a mental model of space into a physical, shareable diagram. It answered the question of where we are in the grand scheme, establishing a reference point from which all other places could, in theory, be related. But for an empire to function, for taxes to be collected and armies to march, you needed more than a symbolic circle, you needed measured reality on the ground. This demand for practical, repeatable precision reached its zenith with the Roman, the land surveyors who were the unsung engineers of empire. Their tool was a deceptively simple device that revolutionized landscape. Imagine a vertical staff with a horizontal crossbar, from which plumb lines were hung at each end. By sighting along the lines of 2 opposing plumbs, a surveyor could establish a perfectly straight line or a right angle over immense distances. This was the tool that laid the backbone of the Roman world, their legendary road network. The process began with the surveyor setting his and aligning its sight lines with a distant landmark. Assistants would then march forward, placing markers exactly along that invisible line, conquering hills and valleys not by going around, but by plotting a relentless, direct path. When a hill obstructed the view, they would use a series of aligned poles, much like to keep the line true. The result was those arrow-straight Roman roads, engineering marvels that bound the empire together with an efficiency that would not be seen again in Europe for over 1,000 years. But this true legacy is etched into the very farmland of Europe and North Africa in a practice called. When the Romans conquered new territory, they did not just build roads, they reorganized the earth itself. They would first establish two main perpendicular axes, a north-south line called the Cardo and an east-west line called the. They would then extend this grid across the entire landscape, dividing it into perfect squares, each called a, measuring approximately 700 meters on a side. This was not merely property division, it was the imposition of Roman order, a geometric template stamped onto forests, marshes, and plains. Each square was parceled out to veteran soldiers or settlers, creating instant, orderly communities and taxable plots of identical size. You can still see this ghostly grid today in the countryside of Italy, France, and Tunisia, where modern field boundaries and roads often follow those original Roman lines laid down too ago. The work of the demonstrates that ancient precision was not solely for the gods or the dead. It was a living, breathing tool of administration. It turned the chaotic wilderness into a measured, productive asset. Their straight roads reduced travel time for legions and merchants, while their uniform land grids law and agriculture. This was surveying scaled to the level of civilization, proving that the principles of alignment and geometry, when applied systematically, could shape not just monuments, but the daily lives of millions and the very fabric of continents. Yet this mastery of terrestrial space through tools like the invites a final, humbling comparison. If Roman surveyors could grid a province with such exactitude using simple plumb lines, how did other cultures, completely isolated from them, achieve feats of measurement that seemed to defy the very tools they had available? The Roman grid was a declaration of order upon the land. But on the boundless Pacific Ocean, an ancient people mastered a world with no fixed landmarks at all. For the Polynesian voyagers, surveying was not about marking territory, but about reading a living, moving map written in the language of nature itself. Their canvas was the open sea, stretching for thousands of miles, and their challenge was the ultimate test of wayfinding, to navigate from one tiny island to another across an ocean that appears utterly featureless. They accomplished this without magnetic compasses, without written charts, and without any of the tools we have previously explored. Their precision came from a profound, generational literacy in the subtle cues of the ocean and the sky, a knowledge system so complete it turned the vast unknown into a familiar pathway. This was not just navigation, it was a different form of global surveying, one that measured distance not in cubits or miles, but in the flight of a bird and the rhythm of a swell. At the heart of their art was celestial navigation, a shared principle with pyramid builders and stone circle architects, but taken to its most dynamic extreme. They memorized the star compass, a mental map where specific stars rose and set at precise points on the horizon, acting as celestial signposts. They knew that as they sailed, these rising and setting points would shift, creating a moving reference frame that told them their latitude and direction. But the stars were only part of the story. During the day, or under cloudy skies, they turned to a science few other cultures ever mastered, the reading of ocean swells. Experienced navigators known as could feel the direction and interaction of multiple wave patterns through the motion of their canoe. A dominant swell generated by a distant weather system would provide a constant directional baseline. When this swell reflected off an unseen island dozens of miles away, it created a subtle, intersecting pattern in the water. By sensing these complex interferences with their hands, or by laying down in the canoe to feel the vessel's motion, the navigator could detect the presence of land long before it was visible, charting a course toward it through wave signatures alone. The environment itself became their guide. They observed the habits of specific seabirds, knowing that certain species would fly out from their home islands to fish each morning and return each evening. Spotting these birds and noting the direction of their flight at different times of day gave them a living radius of detection. They watched for changes in cloud formations, as stationary clouds often gather over the warm air rising from an island, or for the specific color of the water, which could shift with depth and the presence of coral reefs. Every sensory input was a data point in a continuous, dynamic calculation. This immense body of knowledge was not stored in books or on stone tablets, but in living memory, encoded in chants, songs, and intricate stories passed from master to apprentice over years of sacred training. The routes between islands, the star sequences, the descriptions of wave patterns, all were woven into oral traditions that made the information unforgettable. A single chant could be a sailing directive, a map, and a historical record all at once. This method of preserving spatial knowledge through narrative ensured its survival across generations, making each successful voyage a reaffirmation of ancestral wisdom. When a voyaging canoe finally sighted its target island after weeks at sea, it was the culmination of this holistic science. It proved that human beings could achieve staggering navigational precision by becoming deeply, intimately attuned to the natural world. The Polynesian expansion across the Pacific, reaching and settling islands from Hawaii to New Zealand too, stands as one of humanity's greatest exploratory achievements, all guided by this instrumental form of global surveying. It expands our definition of the craft entirely, showing that precision is not always about imposing geometric order upon the land, but can also be about developing a fluent, responsive conversation with the sea and the sky. This deep environmental intelligence allowed them to find their way across a trackless ocean, but it also connects to a final, unifying thread. Whether on land or sea, these ancient experts shared a common foundation, a way of seeing the world that modern technology has largely eclipsed. What was the core mindset that enabled such diverse cultures to each achieve their own form of global precision? The vast Pacific was charted by memory and sensation, but in the quiet depths of the Mediterranean, a different kind of mind was at work. While most ancient tools were extensions of the body or direct readings of nature, a single, astonishing discovery suggests another path entirely, a path of intricate gears and calculated predictions. Recovered from a shipwreck over a century ago, the mechanism is a corroded bronze puzzle that has forced us to rewrite our understanding of ancient technical ambition. Dated to around 2,000 years ago, this device is not a simple tool. It is a compact, hand-cranked universe. Through a complex assembly of at least 30 interlocking bronze gears, it could model the motions of the sun, moon, and known planets, predict eclipses, and even track the cycle of the ancient Olympic Games. It was, in essence, a portable mechanical almanac of the cosmos, a tangible representation of celestial cycles that could be held in one's hands. For the surveyor or the astronomer priest, such a device would have been transformative. Instead of relying solely on nightly observations or lengthy calculations, one could turn a handle and see the positions of celestial bodies for a future date, allowing for the precise planning of alignments, festivals, or navigation windows. The mechanism embodies a leap from observing the sky to simulating it, a shift from reactive measurement to proactive prediction. Its very existence whispers a haunting question. Was it a miraculous one-off, the brilliant invention of a single genius in a workshop in Rhodes or Alexandria, or was it a glimpse into a lost world of technical sophistication? The materials tell a story. Gears and plates of bronze can survive centuries under the sea, but what about the tools that were made of more humble stuff? Imagine a master surveyor's kit, not of stone and metal, but of finely crafted wood, parchment, and wax. A complex geared device made primarily of oak and ash, used to calculate angles or model land gradients, would have rotted away to nothing in a few generations. Detailed maps painted on treated animal skins showing star paths or coastal contours, would have been fragile and perishable. Instruction manuals for advanced geometric techniques, written on papyrus scrolls, could be lost to a single fire or the slow decay of time. The mechanism survives precisely because it was made of durable bronze and was lost in a protective environment. How many other intellectual instruments, equally advanced but crafted from organic materials, have simply vanished from history, leaving no trace for archaeologists to find? This idea opens a door to a different interpretation of ancient precision. Perhaps the flawless alignments and massive scaled projects we marvel at were not achieved solely with the simple tools we have found, but were supported by a hidden layer of sophisticated, perishable technology, a lost software to complement the surviving hardware. The Romans had portable sundials of intricate design. The Chinese developed early forms of the magnetic compass for divination and later for orientation, and cultures across the world used counting boards and abacuses for complex mathematics. These are all echoes of a pervasive drive to build machines that think, to create external aids for the human mind. The mechanism stands as a stark, physical rebuke to any assumption that ancient knowledge was purely intuitive or static. It is a testament to a lineage of thinkers who sought not just to understand patterns, but to mechanize them, to build a working model of reality itself. Its silent gears challenge us to wonder what other conceptual tools, now dust, once guided the hands that measured the world. The silent gears of the mechanism represent a pinnacle of abstract thought, but its creation, and every monumental achievement we have seen, rested on a far more human foundation. A single brilliant mind with a perfect blueprint is powerless without a civilization to bring that vision to life. The true engine behind ancient global precision was not just geometry or astronomy, but the immense, coordinated force of organized society itself. To transform celestial alignments into stone, or to etch perfect lines across miles of desert, required the synchronized effort of thousands, managed with an administrative sophistication that rivals the projects it produced. This was a world without cranes, without trucks, without instant communication. Every block of the Great Pyramid, every mile of a Roman road, every shaped stone at Stonehenge was moved, lifted, and placed by human hands guided by a shared purpose and a meticulously structured chain of command. The logistics alone boggle the modern mind. Consider the provisioning. A workforce of 20,000, as some estimates suggest for the pyramid builders, required not just shelter, but a constant, massive supply of food, water, and tools. Archaeological evidence at Giza reveals bakeries capable of producing thousands of loaves daily, breweries for beer, which was a dietary staple, and entire settlements built for skilled workers and their families. This was not slave labor driven by a whip, as outdated narratives suggested, but a rotating, professionalized workforce, often farmers who worked on the monuments during the Nile's flood season when their fields were underwater. They were compensated with bread, beer, and other goods, turning a national project into a form of social welfare and civic duty. The organization was military in its precision. Work gangs were divided into crews with names like the Friends of Khufu or the Vigorous Gang, a sense of team identity that fostered pride and efficiency. Overseers managed quotas, scribes recorded deliveries of materials, and a hierarchy of officials ensured that every need, from quarrying limestone to sharpening copper chisels, was anticipated and met. This logistical machine transformed a barren plateau into a humming industrial complex, all to serve a single, decades-long project. Yet, raw manpower and food supplies are useless without the knowledge to direct them. The most vital institution for achieving and maintaining precision across centuries was the system of knowledge transmission. The master surveyor who could find true north using the stars did not learn his craft from a book. He learned it through a sacred, rigorous process of apprenticeship, standing beside his teacher night after night, year after year, memorizing the movements of the constellations, the feel of the merkit in his hands, and the rituals of the stretching of the cord. This knowledge was often considered sacred, a privilege belonging to priestly castes or specialized guilds. In Egypt, the skills of mathematics, architecture, and astronomy were closely guarded within the temple's scribal schools. A young initiate would spend years copying texts, learning the precise formulas for calculating volumes and slopes, and internalizing the religious significance of alignment. The knowledge was encoded in difficult hieratic script, making it accessible only to the educated elite, ensuring both its preservation and its control. This guild system, seen in various forms from Mesopotamian to medieval European stonemasons, served as a living library. Techniques for dressing stone, mixing durable mortar, or casting bronze were not written down in manuals, but passed from master to apprentice through demonstration, repetition, and oral tradition. The apprentice learned not just the how, but the why, the subtle tricks for judging the quality of stone by its sound, or for adjusting a measurement based on the day's temperature. This created an unbroken chain of expertise, where the lessons learned from a mistake on one project were carried forward to inform the next. For knowledge that was written, it was often inscribed in stone or on clay tablets, not for public dissemination, but as a reference for the initiated or an offering to the gods. Mathematical tablets from Mesopotamia show row upon row of practice problems for calculating areas, digging canals, or dividing inheritance, evidence of a formalized educational system for administrators. These institutions, the schools, the guilds, the scribal traditions, provided the stability that tools alone could not. They ensured that the precise length of the royal cubit remained consistent for 500 years. They guaranteed that the method for finding the solstice sunrise was not lost when a single elder passed away. They turned individual insight into collective, enduring wisdom. The true monument, then, is not just the pyramid or the road, but the invisible social architecture that made it possible, a resilient network of roles, rules, and relationships that could coordinate the muscle of thousands with the mind of a master surveyor. This deep cultural stability allowed precision to become a tradition, not just an accident. Yet, this very strength, the passing of sacred knowledge through guarded channels, also contains a poignant vulnerability. What happens when the chain is broken, when the last master forgets the chant, when the final apprentice is never chosen? These immense social structures provided the stability for grand projects. But the surveyor's genius often began with a far simpler act, looking up from the blueprint to the horizon itself. Beyond the tools they crafted and the institutions that supported them, ancient experts possessed a profound literacy in the natural world. They understood that the most permanent and reliable markers were not made by human hands, but sculpted by time and geology. A distinctive twin-peaked mountain on the skyline, the precise fork where two rivers met, a solitary, towering rock that stood sentinel over a valley, these were not just scenery. They were the original geodetic network, a pre-existing grid of reference points etched into the continent itself. By carefully observing and memorizing these natural landmarks, a surveyor could orient himself anywhere within a vast territory. This practice transformed the landscape from a chaotic obstacle into a coherent, living map. In the Andes, the Inca civilization mastered this art of sacred geography. Their empire, connected by a vast network of stone-paved roads, was not laid out on an abstract Cartesian grid. Instead, the roads often followed natural ridges and valleys, but their alignments were frequently tied to specific, distant mountain peaks or apis, which were considered powerful deities. A roadway might be deliberately oriented so that on a certain day, the rising sun would appear to crown a particular sacred summit, turning a journey into a moving ritual. The sites of their most important settlements, were chosen not just for defensibility or resources, but for their dramatic visual relationships with surrounding mountain gods. The architecture was then placed to frame these views, making the built environment a dialogue with the permanent, divine features of the earth. This was surveying as an act of reverence and integration. In ancient Britain, we see a similar principle at work across a different landscape. Many Neolithic burial mounds and stone circles are positioned with clear lines of sight to prominent hills or notches in the distant hills. Hill, the largest human-made mound in prehistoric Europe, is not an isolated monument. It sits within a complex ritual landscape where the surrounding hills form a natural amphitheater, and the mound itself is aligned with other sites across the terrain. The builders did not see an empty plain to be filled. They saw a canvas already painted with meaning, and they added their marks to continue the conversation. This method created a durable and meaningful map that persisted for long after the names of kings were forgotten and the purpose of rituals faded. The mountain and the river remained. A traveler centuries later, knowing the old ways, could still use those same peaks to find a sacred spring or a forgotten temple foundation, because the map was the land itself. This environmental literacy required a deep, intimate familiarity with place, gained over generations of observation. It meant knowing how the light struck a certain cliff face at the winter solstice, or how a particular bend in the river marked a boundary between territories. The surveyor's role was to decode this existing language of the land and then inscribe the human story within it, using architecture to highlight and honor the natural markers. In doing so, they achieved a form of permanence that mere mortar could not provide. A stone wall can crumble, but a line of sight to a mountain endures for as long as the mountain stands. This practice reveals a worldview where humanity was not separate from nature, but a participant within a larger, ordered system. The precision they sought was not just technical, it was harmonic, ensuring that human settlements resonated with the enduring features of their world. Yet, this deep reliance on natural markers leads to one of the most poignant mysteries in the entire story of ancient surveying. What happens when the knowledge of how to read this landscape map is lost, when the meaning behind the alignments fades from memory, leaving behind only silent stones pointing at forgotten peaks? The flawless stone and the unwavering line were expressions of a far deeper conviction. For the ancient master builder, a misplaced angle or a misaligned foundation was more than a construction error. It was a tear in the fabric of reality itself. Their drive for precision sprang from a profound philosophical bedrock, the belief that the universe operated on principles of perfect, mathematical order, and humanity's highest calling was to replicate that celestial harmony here on Earth. This was not architecture, it was cosmology in stone. Every act of surveying, from the stretching of the cord in Egypt to the of Roman fields, was a ritual of participation. They saw the cosmos as a grand, intelligible system, what the Egyptians called T, a concept encompassing truth, balance, and the fundamental order of creation. The predictable paths of the stars, the reliable cycles of the seasons, the geometric perfection they perceived in celestial movements, all pointed to a universe built on reason. Their temples, cities, and monuments were attempts to build a microcosm, a small, perfect model of that greater cosmic order. By aligning a temple doorway to the solstice sunrise, they were literally bringing the sun into the heart of their community, marrying the rhythm of the gods to the rhythm of daily life. The grid pattern of a planned city was not just efficient, it was a terrestrial echo of the imagined grid of the heavens, bringing the stability of the stars down to the chaos of human settlement. This worldview imposed an immense responsibility. If a building was meant to be a conduit for divine harmony, then any flaw in its execution was a spiritual failure, a potential source of cosmic imbalance that could bring misfortune or divine displeasure. This is why the role of the surveyor was often sacred, intertwined with priesthood. In Egypt, the ceremony of stretching the cord was overseen by goddess of writing and measurement, and the pharaoh himself often performed the ritual. The act of laying the first foundation line was as much a prayer as it was a technical procedure. The extreme attention to detail we see in the minuscule error of the Great Pyramid's alignment was not driven by a fear of the overseer's wrath, but by a reverence for the axis of the world. A mistake was not simply a blemish on a resume, it was an offense against the very principles that held the world together. We can see this philosophical drive manifest in cultures separated by vast oceans. In China, the ancient practice of geomancy, known as guided the placement of cities, tombs, and homes. It was a complex system for aligning human structures with the invisible energies of the earth and cosmos, ensuring health, prosperity, and harmony. The orientation of the Forbidden City in Beijing, its layout, and the placement of its gates follow these principles meticulously, designed to maintain balance between heavenly and earthly forces. Similarly, the Maya and Aztec cities were laid out as the Great City of, with its central Avenue of the Dead, aligned precisely 15.5 degrees east of north, is thought to mirror specific celestial patterns, perhaps the Pleiades star cluster, embedding a map of the heavens into the urban plan. The pyramid structures represented sacred mountains, portals between realms. This philosophical foundation answers a lingering question about the immense effort expended. Why go to such extraordinary lengths for alignments that many ordinary people might not even consciously perceive? The answer is that the precision was not primarily for human admiration, it was for cosmic validation. It was a statement of belonging, a declaration that this human place was rightful, ordered, and sanctioned by the deeper laws of existence. When the dawn of the equinox slid perfectly through the temple gate, it was the universe itself nodding in approval, confirming that the community was in its proper, harmonious place. This pursuit of cosmic order through earthly precision may seem a distant, ancient mindset, but it invites a very modern reflection. In our quest for ever more digital and automated accuracy, have we lost something of that deeper connection between the act of measurement and a sense of meaningful place? That profound reverence for cosmic order makes their few, subtle mistakes all the more telling. For all their genius, the ancient surveyors were not infallible, and their works were not perfect. The slight deviations we find, the projects abandoned mid-construction, the units of measure that drifted from one city to the next, these are not failures of their legacy. They are vital clues, humanizing signatures that reveal the immense practical challenges they wrestled with in real time. The 3/60ths of a degree error in the Great Pyramid's alignment is a whisper of limitation. Over such a vast base, even a minuscule error in sighting a star, a tiny shift in a foundation stake, or the imperceptible settlement of the bedrock over decades could accumulate into that barely measurable drift. This was not a lack of care. It was the friction of the physical world against an ideal plan. The stones themselves had a say. On an even grander scale, we find projects that ambition. The unfinished obelisk in the Aswan quarries of Egypt is a breathtaking example. This giant shaft of granite, which would have been the largest ever erected, lies still attached to the bedrock, its lower face cracked and abandoned. It shows us the entire extraction process, from the channels painstakingly pecked out around it to the fatal flaw that halted work. Here, the surveyors and quarry masters encountered a problem their planning could not solve, a hidden weakness in the stone itself. The project was not a failure of knowledge, but a sobering lesson in the limits of material and perhaps of time, a monument to ambition meeting an immovable reality. Even the very language of measurement, so carefully guarded, was subject to the drift of distance and time. The royal cubit of Memphis was the standard, but as the knowledge of its exact length traveled to distant provinces or was replicated by local craftsmen over generations, small variations inevitably crept in. A cubit rod in a Thebes workshop might be a hair's breadth shorter than the master standard, and over the course of a large building, that tiny difference could compound. This is why archaeologists sometimes find slight discrepancies in the dimensions of structures from the same period, evidence not of incompetence, but of the challenge of maintaining perfect consistency across a vast kingdom without instant communication. These imperfections pull back the curtain on the workshop floor. They show us teams troubleshooting a cracked foundation trench after an unexpected rain, or a master surveyor making a pragmatic, on-the-spot adjustment to a plan when the terrain proved more stubborn than the map. They remind us that these were not gods laying down lines, but skilled professionals working with heavy materials, under the pressure of seasons, and sometimes under the gaze of an impatient pharaoh. The abandoned project, the slightly wandering wall, the regional variation in a unit, these are the fingerprints of the human hand in the process. They make the achievement more authentic, not less. For in seeing where they struggled, we better appreciate the staggering coordination it took to succeed so often. It underscores that their precision was a hard-won victory over a resistant world, a dialogue between flawless celestial theory and the gritty, unpredictable reality of earth, stone, and time. This honest look at their limitations leads to a final, inevitable question. If their methods were so robust, grounded in nature and refined over centuries, why did this deep, integrated knowledge not simply continue to evolve in an unbroken line to the present day? What happened to this way of seeing the world? These subtle imperfections reveal a craft grounded in earthly reality, yet the echoes of their work resonate in places they could never have known. A truly haunting pattern emerges when we look at the world map of ancient achievement. The Great Pyramid at Giza aligns to the cardinal directions with breathtaking accuracy. Thousands of miles away, across an ocean that neither culture could cross, the Pyramid of the Sun in Mexico is also aligned with remarkable precision, just a fraction of a degree off true north. In Cambodia, the vast temple complex of Angkor Wat is laid out on a strict east-west axis. From the stone circles of Britain to the processional avenues of ancient China, a recurring theme appears, a deep, cross-cultural drive to orient sacred architecture to the fundamental directions of the cosmos. How do we explain this? How did cultures separated by vast continents and oceans, with no evidence of trade routes or shared language, arrive at such similar architectural principles? This is one of history's most captivating puzzles, and it invites us to consider three compelling possibilities. The first is independent invention, the logical outcome of brilliant minds confronting the same universal problems. Every human civilization, from its very beginning, looks to the sky. The sun rises and sets, the stars wheel in their predictable paths, and the seasons turn. For any society seeking to build something permanent, to plant crops reliably, or to honor the forces of nature, mastering these cycles was not a choice, it was a necessity. The most stable, logical reference points for any large construction are the cardinal directions derived from the sun's path. True north, found by observing the fixed point around which the stars rotate, provides an unchanging axis. Aligning a temple to the solstice sunrise creates a powerful, repeatable connection to the cycle of the year. It is entirely plausible that intelligent observers in Egypt, in Mexico, in Cambodia, each independently looked up, recognized the same celestial order, and decided to mirror it in their most important buildings. They were not copying each other, they were each having the same brilliant conversation with the universe. The second possibility delves into the fabric of the human mind itself, a shared intuition for geometry and proportion. The circle, the square, the triangle, these are not just shapes we invented, they are fundamental forms we discover in nature, from the cross-section of a tree trunk to the hexagonal cells of a honeycomb. The human brain seems wired to find balance, symmetry, and right angles pleasing and stable. The 3-4-5 triangle that creates a perfect right angle is a mathematical truth, waiting to be uncovered by anyone experimenting with ropes and stakes. It is a universal key, not a secret code. This innate geometric sense, combined with the practical need to lay out stable foundations, could naturally lead disparate cultures to similar solutions. A builder in Mesopotamia trying to square a temple courtyard, and a builder in the Indus Valley facing the same task might both, through trial and observation, arrive at the method of the Pythagorean triangle centuries before Pythagoras was born. They were tapping into the same bedrock principles of the physical world. But the third possibility is the one that ignites the imagination and fuels endless speculation, the idea of a lost interconnectedness. Could there have been a shared, ancient source of knowledge, a primordial tradition carried by early human migrations that scattered its seeds across the globe, only to be forgotten? Or perhaps, more controversially, could there have been long-distance contact that our current archaeological record has simply not yet uncovered? Proponents of this view point to the sheer specificity of some parallels. The pyramid form itself, a monumental structure with a square base and 4 triangular sides, appears in both Egypt and. Both cultures used them as central elements in their sacred landscapes, often aligning them with celestial bodies. The step pyramid style is particularly striking. While the practical reason for building in tiers, using a stepped platform to reach great heights, is obvious, the symbolic convergence is thought-provoking. Some researchers note similarities in measurement units, like the Maya and ancient Old World cubits, though these comparisons are highly debated and often lack conclusive evidence. The ocean currents and prevailing winds, some argue, could have allowed for accidental or even intentional long-distance voyages that left no durable trace. A single boat lost at sea would leave no archaeological footprint, but a surviving navigator could have carried ideas. This is the realm of what historians call diffusion versus independent invention. The mainstream academic view strongly favors independent invention, emphasizing the immense time depth and the clear local evolution of each culture's unique architectural style, religious beliefs, and construction techniques. The Egyptian pyramid evolved from simple rectangular tombs called mastabas. The pyramid evolved from earthen platforms used for ceremonial gatherings. Their paths to a similar form were long, separate, and deeply rooted in their own worlds. Yet, the mystery persists because it speaks to a deeper yearning. We see in these silent, aligned stones a reflection of a unified human spirit, a shared desire to find order, meaning, and connection in a vast and mysterious cosmos. Whether the explanation is practical, psychological, or profoundly lost to history, the result is the same, a testament to the universal human impulse to measure, to build, and to reach for the stars. This global echo of precision ultimately leads us to a more intimate question, one not about stones and stars, but about the minds that orchestrated them. Who were these master surveyors, and what was it truly like to see the world through their eyes? The silent stones point not just to the sky, but to a hidden language of numbers. Behind every perfect alignment and precisely scaled monument lay a sophisticated command of mathematics, far beyond the simple geometry of ropes and stakes. This was the silent engine of their precision, the system that allowed them to calculate not just angles, but time, space, and the very cycles of the cosmos. For these ancient cultures, mathematics was not an abstract academic exercise. It was a living, breathing tool as vital as the chisel or the plumb line. Their number systems, born from practical necessity, evolved into frameworks capable of modeling reality itself. Consider the Babylonians, who thrived in Mesopotamia over 4,000 years ago. Their choice of a base 60 number system might seem odd to us, accustomed to base 10, but it was a stroke of genius for their needs. The number 60 is beautifully divisible by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This made calculations involving fractions, areas, and the division of commodities like grain or land incredibly efficient. But its true power was revealed in their observation of the heavens. They divided the circle into 360 degrees, 6 times 60, a convention we still use today. This meshed perfectly with their astronomical records, allowing them to track the movements of planets and predict lunar eclipses with remarkable accuracy. For a surveyor, this system meant that calculating the angle of a shadow, the slope of a canal, or the division of a field into equitable plots could be done with a clarity an ease that a more cumbersome system would have hindered. Their mathematical tablets are filled with practical problems, like calculating the amount of earth to be moved for a canal or the length of a diagonal across a rectangular field, proving that their arithmetic was always in service to shaping the world. Across the ocean, the Maya have developed a mathematical system of breathtaking elegance and power, entirely independently. They used a base 20 system, likely originating from counting on both fingers and toes, and they possess something revolutionary, a concept of zero. Their zero was not just a placeholder, but a fully realized number used in complex calculations. This abstract leap allowed them to perform advanced arithmetic and create their famed long count calendar, a system so precise it could count days in a continuous sequence over thousands of years. For the Maya, time was a sacred geometry, and their mathematics was the tool to map it. Their calendar wasn't just for marking seasons, it was used to schedule grand construction projects, to determine the auspicious moments for laying a cornerstone or dedicating a temple pyramid. The sheer scale and coordination of their city-states, with pyramids aligned to solar and Venusian cycles, would have been impossible without the predictive power of this calendrical mathematics. They could calculate the synodic period of Venus, the 584 days it takes to return to the same position relative to the Sun, and use that knowledge to time rituals and perhaps even the orientation of buildings. This connection between number, time, and space is the key. Mathematics provided the bridge between the observed celestial event and the terrestrial plan. A Babylonian astronomer priest could use his base 60 tables to predict the next solstice, and the surveyor would then know exactly which day to mark the sunrise point on the horizon. A Maya calendar keeper could calculate the future position of a planet, and the architect could design a doorway to frame its rising on that specific date. On a more immediate, physical level, mathematics enabled the critical logistics of any large project. Calculating the volume of a stone block told you how many workers were needed to move it. Computing the area of a pyramid's base told you how much paving material was required for its courtyard. Determining the consistent, gentle slope of an aqueduct, a drop of perhaps 1 foot in every 100, required repeated division and measurement to ensure the water would flow without stagnating or rushing violently. These were not guesses, they were the results of applied arithmetic, often recorded on tablets or in codices that served as the project's technical manual. The development of these advanced number systems, from the divisibility of 60 to the conceptual power of 0, represents a parallel monument to the stone ones. They are monuments of the mind, frameworks that allowed human thought to grasp complexity, project into the future, and execute plans of staggering scale and duration. The precision in the stone is a reflection of the precision in the calculation. So we see a pattern emerge, from the celestial to the geometric, and now to the numerical. But this raises a final, intimate question. If their knowledge was so profound, so embedded in their institutions and etched into their landscape, why did the bright thread of this understanding eventually fray and fade in so many places? What happens when the calculators fall silent? The silent calculations of the Maya and Babylonians found their ultimate expression not on tablets, but in stone, aligned to the moving clock of the heavens. This is where the science of archaeoastronomy enters the story, acting as a translator for a lost language. By meticulously measuring the orientations of ancient monuments against the sky, this field provides the definitive physical evidence that their precision was deliberate, repeatable, and profoundly intelligent. It transforms monuments from mysterious ruins into calibrated instruments, their stillness holding a record of celestial motion. Take the Great Passage Tomb in Ireland, older than the pyramids of Giza. For most of the year, its long, narrow entrance corridor lies in deep shadow. But for a few precious minutes around the winter solstice sunrise, a brilliant shaft of sunlight pierces the darkness, traveling up the passage to illuminate the inner chamber in a golden burst. This is not a vague alignment or a happy accident. Modern measurements confirm the roof box above the entrance was engineered with exacting care to create this narrow window of light, lasting only about 17 minutes each year. The builders, 5,000 years ago, planned for the sun's lowest, weakest point in its annual cycle and designed a structure to capture and magnify its power at that precise moment. This was a statement written in light and shadow, a way of bringing the reborn sun into the heart of a tomb, linking the cycle of the seasons with the cycle of life and whatever lay beyond. Across the Atlantic, in the high desert of Canyon, another precise solar marker speaks of a deep, observational tradition. On Butte, 3 large stone slabs lean against the cliff face. Behind them, a spiral petroglyph is carved into the rock. For most of the year, patterns of light and shadow dance around it. But on the summer solstice, a dagger of sunlight, perfectly sliced by the edges of the slabs, pierces the center of the spiral. At the winter solstice, 2 daggers of light bracket the spiral on either side, and at the equinoxes, a smaller, central dagger appears. This sun dagger site is a sophisticated calendar in rock, its creators using the natural architecture of the slabs to create a predictable, annual light show that marked the critical turning points of the year. The precision required to position those ton slabs so their edges would create such specific solar effects at the exact right moments is staggering. It shows a community that observed the sun's path not for 1 year, but for generations, patiently noting its incremental shifts along the horizon until they could predict its behavior and then permanently encode that knowledge into the landscape. These are not isolated examples. In Egypt, the temple was so precisely oriented that twice a year, the rising sun would reach over 60 meters into the mountain-carved sanctuary to illuminate the statues of the second and the sun god Ra, leaving the other gods of the underworld in shadow. At Angkor Wat in Cambodia, during the spring equinox, the sun rises directly over the central temple tower, an alignment baked into the very axis of the world's largest religious monument. What archaeoastronomy reveals is a global pattern of intent. By using precise surveying tools to map these alignments and then running computer models to reconstruct ancient skies, researchers can rule out coincidence. The statistical likelihood that so many major monuments from so many different cultures would by random chance point to significant solar, lunar, or stellar events is vanishingly small. The stones themselves confess their purpose. This scientific validation is crucial. It moves the discussion beyond speculation and into the realm of demonstrated knowledge. It confirms that the ancient surveyors and architects were not just building shelters or tombs, they were constructing 3-dimensional observatories and permanent calendars. They were creating mechanisms, without moving parts, to track time on a scale that connected the human community to the cosmic order. Each solstice sunrise each dagger of light at Canyon was a confirmation that their model of the universe was correct, that their precise measurements had successfully harnessed a moment of cosmic time. This turns our gaze from the monument to the mind behind it, to the individual who could translate a lifetime of watching the horizon into an immutable design in stone. But if their knowledge of the skies was so exact, so beautifully recorded in architecture, it forces us to confront a poignant and inevitable question. What happens when the culture that nurtured this precise vision changes, when the meaning behind the alignment is forgotten, leaving only the silent, waiting stones? The stones have told their story, but how can we be sure we are hearing it correctly? To move beyond theory and into the realm of lived experience, we turn to a field where history is not just studied, but physically remade. Experimental archaeology asks a beautifully direct question: what happens if we try to do it ourselves? By reconstructing ancient surveying methods using only the tools and materials available at the time, researchers and dedicated enthusiasts have transformed dusty hypotheses into tangible, often humbling, reality. These are not simulations on a computer screen. They are hands in the dirt, rope burn, and sweat experiments that test the very limits of what we believe was possible. One of the most visceral demonstrations involves moving the unmovable. For generations, the transportation of Stonehenge's bluestones, each weighing several tons, from the hills in Wales to Salisbury Plain over 150 miles away, seemed an almost supernatural feat. Theories ranged from glacial movement to lost advanced technology. Then, teams of experimenters decided to try the most straightforward and most grueling method: human power and simple engineering. They simmer stones using only stone mauls and fire setting, a process where heated rock is doused with water to crack it. Then came the real test, the journey. They built a wooden sled and placed a ton stone upon it. Using ropes fashioned from natural fibers, a team of around 20 people found they could pull this immense weight over greased wooden tracks. To cross waterways, they constructed a replica of a prehistoric log boat, a daunting task of hollowing out a massive oak trunk, and discovered that such a vessel could indeed float a bluestone across the Bristol Channel. The experiment did not prove this was exactly how it was done, but it proved something more important, that it could be done with Neolithic technology, organization, and sheer determination. The journey would have been a monumental logistical saga, not a mystery of lost science, but a testament to communal will and practical skill. Beyond moving stones, experimental archaeologists have tested the very act of seeing like an ancient surveyor. To understand celestial alignment, you must first clear away the light pollution of the modern world, both literal and metaphorical. Teams have gone into remote fields with nothing but wooden stakes, lengths of hemp rope, and a clear night sky. Attempting to recreate the Egyptian method of finding true north using 2 stars, they quickly encounter the real-world challenges the ancients faced. A slight breeze makes the plumb line of a Merkit sway. The human eye strains to judge the exact moment a star reaches its highest point. The process is slow, requiring multiple nights of observation and minute adjustments to the alignment of stakes in the ground. Yet, when persistence pays off, and a line is established that holds true against modern instruments, the result is a profound sense of connection. It reveals that the precision of Giza was not gifted by some unknown device, but earned through patient, repeatable technique and a deep familiarity with the night sky that few of us today can comprehend. These experiments often yield surprising, counterintuitive insights. One team investigating how the lines could be laid so straight over miles of terrain tried the aligned pole method. They discovered that over long distances, the curvature of the Earth itself becomes a factor. A line of straight poles will not actually point at the same horizon marker because the Earth curves away beneath them. This forced a refinement of the theory, suggesting the surveyors likely worked in shorter, more manageable segments, constantly re-establishing their sight lines from intermediate high points, a technique requiring even greater spatial awareness and planning. Another experiment focused on the acoustic properties of ancient sites. Researchers using simple percussion instruments at places like the Hypogeum in Malta or in Peru have found that certain chambers and tunnels are tuned to specific resonant frequencies, creating disorienting or awe-inspiring sound effects. This suggests that the surveyors and architects may have been attuned to sound as well as sight, designing spaces where acoustics were part of the ritual experience, a dimension of precision we can only appreciate by being physically present and listening. The value of this hands-on research is immeasurable. It cuts through centuries of speculation and romanticism. When a modern team fails repeatedly to move a stone with a proposed method, it tells us that method is probably wrong. When they succeed, it opens a window into the past that no written record ever could. We feel the strain on the ropes, the frustration of a cloudy night ruining observations, the triumph of a perfect alignment finally achieved. It grounds the awe-inspiring achievements of antiquity in the reality of human ingenuity, patience, and collaboration. These experiments remind us that the ancient master builder was not a wizard, but a supremely competent professional, solving immense problems with the tools at hand. Yet, for all these physical recreations, a deeper mystery remains untouched by rope and stone. We can replicate the how, but can we ever truly recover the why, the inner world of meaning that transformed a technical act into a sacred duty? The echoes of their experiments are not confined to history books or remote fields. We live inside the legacy of those ancient surveyors every single day. The invisible grid that organizes our modern world, the very framework of maps, property lines, and global positioning, is built upon concepts they first discovered and refined. Our technological present is not a departure from that distant past, but a direct continuation, a story written with ever more precise tools, but guided by the same fundamental principles. Consider the simple act of looking at a digital map on your phone. That map is built on a coordinate system of latitude and longitude, imaginary lines that wrap the globe. The idea of dividing a circle into 360 degrees, which gives us those lines, comes directly from the ancient Babylonians and their base 60 mathematics. Their choice was not arbitrary, it was brilliantly practical for calculation, and it became the universal language for measuring angles, a language we still speak. When a modern surveyor uses a theodolite to measure an angle for a new bridge, or when a satellite calculates its orbital position, they are relying on a conceptual framework that is over 4,000 years old. The method of triangulation, using a known baseline and angles to determine an unknown distance, is the cornerstone of modern land surveying, satellite geodesy, and even the way your phone calculates its location. This is not a modern invention. It is the same geometric logic the Egyptians used to measure land after the Nile's flood, and the same principle Eratosthenes scaled up to measure the Earth itself. Our global positioning system is, in essence, a celestial navigation network of incredible sophistication, but its core function, using known reference points to pinpoint a location in space, is the same problem Polynesian navigators solved by reading the stars and swells. The tools have changed from Merkit and Gnomon to atomic clocks and orbiting satellites, but the underlying intellectual architecture, the need to establish position relative to fixed points, remains unchanged. This legacy extends beyond measurement into the very philosophy of how we shape our environment. The Roman practice of imposing a geometric grid upon the landscape for organization and equity finds its echo in the uniform street grids of modern cities from New York to Barcelona. The ancient drive to align structures with cosmic events, while no longer a common religious practice, is mirrored in our most ambitious engineering projects, where precision is paramount. The alignment of a particle accelerator, the orientation of a radio telescope listening for whispers from the cosmos, or the trajectory calculation for a Mars rover, all demand a level of exactitude that would feel deeply familiar to the master builders of Giza. They would understand the obsession with eliminating error, the painstaking calibration, and the profound respect for the laws of nature that such projects require. Their work laid the foundational stones, not just of temples, but of a way of thinking, a belief that the world is measurable, understandable, and can be interacted with through reason and careful observation. By understanding their ingenuity, we gain more than historical trivia, we gain a deeper appreciation for the long, unbroken thread of human curiosity. It connects the student in a geometry class today, learning about triangles, to the surveyor stretching a rope along the Nile 5,000 years ago. It links the engineer programming a drone to map a coastline with the Polynesian navigator feeling the pulse of the ocean's swell. Our technological marvels are not a break from ancient wisdom, but its flowering. We have externalized their knowledge into silicon and steel, but the core impulse, to map our place in the world and to build upon it with precision, is a timeless human signature. This realization invites a final, quiet reflection. If their methods, born of patience and deep connection to the natural world, could achieve such enduring results, What might we be overlooking in our rush for ever faster, more automated solutions? Such profound human achievement deserves to stand on its own merit, free from the shadow of sensational myth. The story of ancient precision is so compelling that it has, over time, attracted layers of speculation that often obscure the true marvel. We hear whispers of lost super-civilizations wielding impossible power, or of otherworldly visitors providing advanced blueprints. These narratives can be captivating, but they share a common, subtle flaw. They diminish the very people whose ingenuity we seek to celebrate. The evidence, patiently gathered by generations of archaeologists and historians, tells a different and far more empowering story, one of human intelligence solving immense problems with the tools at hand. Consider the claim that the stones of the Great Pyramid were cut with lasers or some form of lost high technology. The archaeological record tells a more tangible, and no less impressive, tale. In the quarries surrounding Giza, researchers have found thousands of stone and copper tools, the very chisels and pounders used by the workers. They have uncovered simple but effective methods, like driving wooden wedges into natural cracks in the limestone and soaking them with water, causing the wood to expand and split the rock with tremendous force. They have identified the use of abrasive sand, harder than the copper saws available, to cut through granite by simple, relentless friction. These are not the tools of a magical, vanished science. They are the tools of a supremely organized society applying known physics with monumental patience. The precision came not from a single miraculous device, but from the cumulative skill of countless artisans checking their work against master templates and calibrated chords. Another persistent myth suggests that the lines could only have been designed by beings who could fly, as the full forms are invisible from the ground. This overlooks the elegant, low-tech solutions we have already explored, like proportional scaling with a ground-level grid. But it also ignores a simple, profound fact about human perception. The surveyors did not need to see a 500-foot hummingbird as a complete picture to create it. They only needed to execute each small segment of the design with local precision, following a master plan broken into manageable parts. A team leader standing on a nearby foothill could easily oversee the work, guiding the adjustment of a line to ensure its curve was true. The achievement is in the coordination and the plan, not in a single impossible viewpoint. The most pervasive myth of all is the idea of a single, global mother civilization that taught pyramid building to the world. This theory, often called hyper-diffusion, suggests that a sophisticated culture like Atlantis traveled the globe, seeding knowledge everywhere from Egypt to Mexico. While the human desire to find connection is understandable, the archaeological evidence firmly points in the opposite direction, toward brilliant independent invention. Look closely at the pyramids of Egypt and those of. They are profoundly different in purpose, construction, and internal design. Egyptian pyramids were primarily smooth-sided tombs, sealed forever, with internal chambers focused on the journey to the afterlife. Pyramids were almost always stepped platforms for temples, with external staircases leading to active places of worship at the summit. They were built to be climbed, not sealed. Their construction methods differed, their religious contexts were worlds apart, and their stylistic evolution can be traced step by step in their local archaeological records. They represent not a blueprint, but a convergent solution to a universal human impulse, to build a monumental, upward-reaching structure that connects Earth to the heavens. The similarities are a testament to shared human imagination, not to a shared teacher. Why do these alternative narratives hold such appeal? Perhaps because the scale of the actual achievement feels almost too great to accept. It is easier to attribute the work to a mysterious, superior force than to sit with the awe-inspiring reality of what thousands of coordinated, patient, and intelligent human beings can accomplish over generations. The myth offers a shortcut, an answer that requires no further investigation into the intricate social structures, the trial and error, the passed-down knowledge, and the sheer grit that these projects truly demanded. But in choosing the myth, we lose the real story, and we do a deep disservice to our ancestors. We rob them of their genius, their perseverance, and their humanity. The solid ground of evidence, from tool marks and quarry sites to astronomical alignments and experimental reconstructions, paints a picture that is far more satisfying than any fiction. It shows us people not so different from ourselves, looking at the same sun and stars, feeling the same pull to create something lasting, and solving colossal puzzles with creativity, cooperation, and relentless dedication. Their legacy is not a mystery to be solved by outside forces, but a demonstration of human potential written across the globe in stone and earth. This truth invites a more meaningful question, not how did they do it with help from beyond, but what can we learn from their profound connection to the world, their patient observation, and their ability to work together toward a vision larger than any single lifetime, even with all we have learned. The ground beneath our feet still whispers with unanswered questions. For every mystery solved by experimental archaeology or celestial mapping, another lingers, a stubborn puzzle that reminds us the past has not yet yielded all its secrets. These are not gaps in the story, but invitations, frontiers of understanding that continue to drive researchers and captivate anyone who looks upon these ancient works with wonder. They are the places where our modern explanations meet their limits, and we must humbly admit that the full ingenuity of the ancient master builder is not always fully within our grasp. Consider the colossal stone platform at Baalbek in modern-day Lebanon, known as the Here, 3 limestone blocks, each estimated to weigh around 800 tons, are fitted together with a precision that seems to defy the physics of the ancient world. That is the weight of 2 fully loaded jumbo jets per stone. We can theorize about the use of massive wooden sledges, armies of workers, and intricate systems of ropes and levers. We can point to Roman engineering prowess, as the site was expanded during their era. But the honest truth is that no existing account or experiment has conclusively shown how such monoliths were from a site nearly a mile away, transported up a gentle incline, and then lifted over 20 feet to sit in a perfect, seamless row. The scale is so extreme it pushes even our most generous estimates of ancient labor and engineering to the breaking point. It stands as a silent, monumental question mark, a challenge to our assumptions about the upper limits of what pre-industrial societies could physically achieve. Similarly, the vast Inca road system, which stretched over 25,000 miles through some of the most treacherous mountain terrain on Earth, presents a different kind of precision puzzle. We understand the why, to bind an empire together with unmatched efficiency. We can see the how in the surviving stonework, the masterful dry stone masonry that locks together without mortar. But the specific surveying methodology for plotting these roads across the vertiginous peaks and deep ravines of the Andes remains elusive. How did their surveyors maintain such consistent gradients and direct routes over distances where the horizon is a jagged line of snow-capped peaks? They had no theodolites, no precise way to measure altitude. One compelling theory suggests they used a form of giant, sighting protractors made of wood and cord to measure angles of ascent, combined with an intimate, generational knowledge of the mountain passes. Yet the exact tools and the step-by-step process for translating a route from a planner's mind onto the side of a cloud-shrouded cliff are a secret the stones have kept. Each perfectly fitted step on the Inca trail is both a testament to their skill and a quiet reminder that we are still piecing together the full picture of their technical mind. These lingering mysteries serve a vital purpose. They prevent us from becoming complacent, from thinking we have the ancient world completely figured out. They are the unanswered riddles that keep the field of archaeology dynamic and alive, driving new technologies like ground-penetrating radar and 3-dimensional laser scanning in the hope of finding fresh clues. More importantly, they guard against arrogance. They remind us that a civilization's deepest knowledge, the nuanced tricks of a trade passed down orally for centuries, can vanish almost completely, leaving only the magnificent, baffling results behind. The unfinished obelisk at Aswan shows us a failure we can understand, a cracked stone. But the completed at Baalbek shows us a success we cannot yet fully replicate, even with all our modern knowledge. That is a profoundly humbling distinction. So these puzzles are not failures of history, but its enduring gifts. They are the open doors, the unsolved equations that beckon to the curious. They ensure that the study of ancient precision is not a closed book, but a living conversation between the present and the past. Every time a researcher stands before those 800-ton blocks or walks the spine of an Inca highway, they are not just looking at what was done, they are listening for the echo of how, an echo that grows fainter with each passing century but has not yet faded into silence. And in that space between what we know and what we still seek, the true respect for those ancient minds continues to grow. The lingering mysteries of Baalbek or the Inca roads are not puzzles for a single expert to solve. They demand a different kind of investigation, one that listens to the land, the sky, and the stories all at once. Unlocking the full story of ancient precision is not a solo act, but a symphony of disciplines, where the astronomer's star chart must speak to the archaeologist's trowel, and the geologist's soil sample must confirm the ethnographer's recorded chant. This is the power of interdisciplinary synthesis, where the isolated clues scattered across time are finally brought together to form a coherent, breathtaking picture. Think of a single ancient site as a crime scene, but one where the crime is creation itself. The evidence is fragmented and layered over. The archaeologist arrives first, meticulously excavating, mapping the foundation trenches, cataloging every tool fragment and pottery shard. They can tell you when the site was built, in what sequence, and with what materials. They find that might have held siding poles or the workers' camp that reveals the project's scale. But on their own, they cannot tell you why the main axis points to that specific notch on the distant horizon. For that, you need using sophisticated software that can rewind the night sky to any date in history, they can calculate what celestial event, if any, that alignment targeted 2,000 years ago. When the astronomer's digital model shows that the axis perfectly frames the rising point of the star Sirius on the founding day indicated by the archaeologist's pottery dating, a powerful link is forged. The static stones suddenly have a date with the cosmos. Yet, the landscape itself holds memories the stones do not. This is where the geologist and the geographer enter. The geologist can analyze the quarry from which the stones were cut, identifying the exact mineral signature. This can trace a monolith at Stonehenge back to its specific outcrop in Wales, confirming the incredible journey it took. The geographer, using satellite imagery and LiDAR technology that can see through forest canopy, can reveal the larger context. What looks like an isolated temple on the ground might, from above, be revealed as the focal point of a vast, processional avenue connecting it to a sacred mountain 10 miles away. This broader view shows the site was not an island, but a node in a ritual landscape, its precision part of a much larger planned geography. But what of the minds behind the measurement? For cultures with no written records, this is the most fragile evidence of all. This is where the ethnographer and the student of oral history become vital. By carefully studying the myths, stories, and traditional practices of descendant communities, researchers can sometimes find echoes of ancient knowledge. A creation story might describe a journey guided by a specific constellation. A traditional farming calendar, passed down through song, might still mark planting times by observing a star's heliacal rising, the same event, and has just linked to a temple alignment. When the ethnographer's recorded chant about the path of the ancestor sun aligns with the astronomer's solstice axis, it transforms a geometric line into a living narrative. It suggests the precision was not just technical, but deeply woven into the community's identity and worldview. This synthesis even extends to the microscopic level. Soil scientists can analyze ancient pollen trapped in construction layers to reconstruct the environment at the time of building, revealing if the site was built in a lush forest or an open plain, which would dramatically affect site lines for surveying. Engineers can run stress simulations on proposed moving techniques, testing if wooden sledges on a certain soil type could actually bear the weight of an 800-ton block. Each field asks its own specialized questions, but the answers only make sense when shared on a common table. The result is a form of respectful triangulation, not just of space, but of human experience. A single fact, like the orientation of a wall, becomes multidimensional. To the archaeologist, it is a construction line. To the astronomer, it is a solar marker. To the ethnographer, it is an axis of myth. All three are true. This collaborative approach guards against the narrow interpretations of any one field. It prevents us from seeing ancient sites only as astronomical observatories, or only as political symbols, or only as religious temples. They could be, and often were, all these things simultaneously. The precision served a unified purpose, blending practical necessity, spiritual belief, and social order into a single, enduring act. This modern, interdisciplinary conversation is, in a way, the final tribute to the ancient master builders themselves. They did not think in separated categories of science, religion, and art. They lived in a world where these concepts were intertwined. By bringing together our fragmented modern specialties, we attempt to reconstruct that holistic vision, to see the world, for a moment, through their unified gaze. It is a reminder that the truest understanding often lies not in the isolated clue, but in the connections woven between them. This symphony of disciplines brings us face to face with a profound responsibility. The very act of seeking to understand these ancient wonders places a weight upon our shoulders, a duty to the stones themselves and to the living cultures that still hold their stories. Our modern world, with its relentless expansion and the sheer volume of our footsteps, poses the greatest threat these sites have ever faced. Preservation is no longer a passive hope. It is an urgent and active science. The challenge is a quiet one, often invisible to the casual visitor. A single touch may seem harmless, but the cumulative effect of millions of hands on a limestone surface transfers oils and acids that slowly, permanently erode carved hieroglyphs. The vibration from a nearby highway, a quarry blast, or even the low hum of constant tourist buses can destabilize foundations that have stood for. The very breath of crowds in a sealed tomb chamber raises humidity, encouraging salt crystallization inside the stone, a process that literally makes the walls crumble from within. This is a conflict of love, where our desire to witness greatness can, if left unchecked, become the agent of its destruction. Beyond the physical strain lies the pressure of development. As cities grow and resources are sought, ancient landscapes are often seen as empty space. A planned mining operation might threaten a sacred mountain alignment, or a new housing development could pave over the subtle ground markings of a forgotten settlement, erasing its story before it is ever read. The fight for preservation is a race against time and competing needs, requiring careful mapping, legal protection, and often difficult conversations about what we value as a global community. Yet, the most delicate dimension of this work is not about stone and soil, but about spirit and memory. For many of these sites, the most vital keys to their understanding are not buried in the ground, but carried in the living traditions of descendant peoples. Engaging with this indigenous knowledge is not simply an academic courtesy, it is an ethical imperative and a pathway to deeper truth. When a researcher studying solstice alignments at a Maya site listens to a local elder describe the same astronomical event within a creation story, that alignment transforms from a geometric fact into a chapter of a living narrative. The elder is not just an informant, but a custodian of a continuous intellectual tradition that stretches back to the original builders. This knowledge is often holistic, weaving together astronomy, ecology, ritual, and social law in a way that our specialized modern disciplines struggle to see. To approach it respectfully means to collaborate, not extract. It means recognizing indigenous communities not as subjects of study, but as partners and rightful stewards. It involves sharing authority, ensuring that research questions are shaped together and that discoveries are interpreted through a cultural lens, not just a Western scientific one. Projects that succeed in this partnership often yield richer, more nuanced understandings. Archaeologists working with Aboriginal communities in Australia, for instance, have learned to read the landscape differently, seeing how the ancient paths of ancestral beings are physically inscribed in the topography and directly influence the placement of art and ceremonial sites. This is a form of precision that no theodolite can measure, a precision of meaning. Our responsibility, therefore, is twofold. We must protect the physical integrity of these places with the best tools of modern conservation, slowing the inevitable decay and shielding them from heedless harm. And we must protect the living knowledge that gives them context and soul, by listening with humility and forging relationships built on mutual respect and shared goals. The ancient surveyors built for eternity, but eternity now depends, in part, on us. They left a legacy in the alignment of stone to star, and we are left with the choice of how we will honor that legacy, whether as curious consumers or as thoughtful guardians in an unbroken chain of wonder. Their legacy is not a collection of forgotten tricks, but a mirror held up to our own age. We stand at the summit of a technological mountain they could not have dreamed of, with satellites that can measure the drift of continents and computers that model the universe. Yet in this very moment of supreme capability, their quiet genius speaks most clearly. They achieved what they did not by looking for answers beyond their world, but by looking more deeply into it. Their precision was born from a patient, lifelong conversation with the environment, a dialogue we have largely replaced with the silent certainty of a digital readout. They asked the horizon for direction and listened to the stars for time, transforming the entire planet into their workshop and the cosmos into their blueprint. This was not a lesser science, but a different kind of knowing, one built on intimacy rather than abstraction. Their greatest tool was not the rope or the gnomon, but the cultivated human mind, trained to see patterns where we might see only chaos, to extract mathematical truth from the arc of a shadow, and to hold a vision steady across generations. This points to a subtle but profound shift in our own relationship with precision. For them, accuracy was a means to an end that was often sacred, communal, and deeply meaningful. A perfect alignment created a moment of awe, confirmed a cultural story, or synchronized a society with the turning of the year. In our world, precision has become an end in itself, a relentless pursuit of smaller tolerances and faster calculations, often divorced from any larger sense of purpose or wonder. We can pinpoint our location on a glowing map with an error of mere feet, yet how many of us could find true north by the stars, or sense the passing of a season by the sun's path across our own wall? Their mastery challenges this disconnect. It asks us to consider what we might be overlooking in our reliance on external, black box technology. What wisdom fades when we no longer need to understand the underlying principles, when we trust the device's answer without knowing the question it solved? This is not a call to abandon our tools, but to remember the minds that first invented their conceptual ancestors. The satellite in orbit and the stone circle on the plain are part of the same human story, a continuous thread of curiosity and the desire to map our place in existence. One represents the externalization of that quest into silicon and steel, the other its internalization into myth, memory, and masonry. Both are testaments to ingenuity, but only one required its builders to personally know the sky. So what is the ultimate lesson etched in these aligned stones and measured landscapes? It is that human potential, when focused by patient observation and unified by a shared vision, is itself the most powerful technology of all. They had no shortcuts, so they cultivated depth. They had no instant communication, so they built institutions of knowledge that could span centuries. They saw the earth and sky not as separate realms, but as a single, intelligible system to which they belonged. In our rush to automate and optimize, we risk forgetting the profound satisfaction and understanding that comes from this kind of direct engagement with the world. Their legacy, therefore, is an invitation. It asks us to look up from our screens, if only occasionally, and recover a piece of that older literacy. To notice where the sun sets on the solstice, to learn a few key constellations, to appreciate the sheer intellectual force required to shape a continent without a single engine. In doing so, we do more than honor them, we reconnect with a fundamental part of our own capacity for wonder and reason. The silent precision of the ancients endures not as a mystery to be solved, but as a benchmark for what is possible when humanity chooses to build in harmony with the cosmos, using nothing but attention, intellect, and the unwavering human hand. Their legacy is a conversation that continues, and your perspective is a vital part of it. If this journey into the minds of ancient surveyors has sparked your own curiosity, we would love to hear from you. Which mystery lingers most in your thoughts? Is it the silent, waiting stones of Baalbek, the celestial clockwork of the mechanism, or the vast, earth-scribed lines of share your reflections in the comments below? To ensure you never miss our next exploration into the hidden threads of history, subscribe to the channel and tap the notification bell. We are just getting started. For those feeling the pull to dive even deeper, we have compiled a list of resources in the description. You will find links to reputable museums offering virtual tour of these incredible sites, academic papers discussing the latest archaeological findings, and citizen science projects where you can sometimes contribute to ongoing research. The story of ancient precision is still being written, with new discoveries emerging every year, and you can follow along as the puzzle slowly comes